entire 90 minutes for practice and not, sorry, let's not record this. Not. So the notes that we were taking is the properties of definite integrals. So properties of definite integrals. And for when you do these practice problems, these properties, when you first start practicing them, they're not going to mean a lot to you. You're just going to maybe look back at your notes and answer the questions and feel like a little bit confused. As we learn more about integrals, it'll be like, that property is actually kind of nice. I might want to use that in the future. So these notes today may not make a lot of sense, but the more we study it, hopefully you'll see the reason why we went over them. So the first one says, if you do the integral from a to b, f of x dx, it's the negative version as if they did the integral from b to a. So if they switched, these are the numbers that are your interval, where b is the bigger number and a is the smaller number. So if you evaluate using b and a, then you should get like a positive answer. But if you go backwards, the backwards version of that would be a negative answer. So you're going the opposite direction. And for today, you're just going to use that property. In the future, you'll understand more of like why that makes sense.
Is this going to be an F?
This is the little integration sign, which is, it's like a slanted line with like little curly cues on the ends. All right, number 2. If I evaluate an integral from a to a, that's just going to equal 0. If you, I did not mean to write fx. If you integrate a constant, so it's not a function, we're integrating just a number, then that's going to be the constant multiplied by b minus a. For this one, if you had one function plus another function, you can split those apart and you can integrate them separately. So you could do f of x dx and then plus or minus g of x. For the next one, if you have a constant in front of your function, then you can just take that constant and move it to the front of the integral. So you just take that and then multiply whatever you get when you do the integration. This is the one that I always forget about. I'll be like, what do I do with that number? Oh, you can just multiply it. And then the last one, if I say that I'm integrating one function from a to b, and I'm adding another function from b to c, then that's exactly the same as if I took the function and just integrated it from a to c instead. Yeah, dx, dx, dx. So here is our first example. We're going to do 3 examples, I think. So first example, we're going to evaluate from 1 to 0, and our function is 4 plus 3x squared dx.
This row.
Yeah.
On number 6, remember get dx behind that. Oh, nice.
I just was zoomed in enough. Huh?
Is there one behind 4 too? I can see. Yeah, there's one behind 4.
This, since it's in parentheses, this is considered to be one function, so it'd just be 4 plus 3x squared, and then...
He's talking about number 4.
Oh, on number 4.
Yeah, that's steps, because I can see the dx.
Yeah. We got it all copied? So I think some of these are maybe common sense. Like these two probably common sense. This one may be common sense a little bit, but I think this one I always have to look back at to make sure. That one, yeah. So it'd be good when you're working on the evaluations today to like have them out in front of you, basically just reference. Okay, so this one says we're evaluating this from 1 to 0, and this is the function we're using. So what I'm going to do is I'm going to think about those properties and just kind of split it apart. So one of the properties was that you can think of this as one function plus another function, so I can split it apart into two functions. So I'm going to say the integral from 1 to 0 of 4 plus from 1 to 0, and if we have 3x squared, what could I do with that 3? I could put it in the front. It's like a constant. So this is kind of like number 5, where you've got a number in the front of your function, so you can move it to the front of your integral, right? So I'm going to put the 3 in the front, and then the x squared right there. Okay. So now let's think about how these work. So what do you do if you're taking the integral of a constant? So constant times b minus a, so times 1 minus 0, plus. And then with this one, we just do 3 multiplied by whatever we get when we take the integral of x squared, right? From 1 to 0. And this is the notation that means what's the area under that curve. And we've actually done this already. What's the area under the curve x squared if you go from 0 to 1? 1/3. Yeah, we did that. We did that in the video, right? Eventually you're going to know how to do these by hand, but we don't quite know yet. So today they're going to be very limited in what they have you do because you haven't learned it yet. But knowing x squared from 1 to 0, that's something we've done already. All right. So if we do the math for this, we've got 4 plus 1, and so what should we say? 5. So if you were to graph this function, 4 plus 3x squared, and then shade in the numbers between the, or not the numbers, but the boxes that are between the curve and the x-axis for the x values from 0 to 1, the area of that would be 5. And that's what this is.
Exact.
And that's exact. That's the exact answer. Exactly 5. Who knew? Interesting. Oh, okay. All right, next one. So this one says if the integral from 10 to 0, or evaluated from 0 to 10, is 17, and the integral from 0 to 8 of the same function is 12, then the same function evaluated from 8 to 10 equals what? So if you have a function and the area of the curve evaluated from 0 to 10, the area underneath the curve is 17. And if you do from 0 to 8, so you're not doing the whole area now, we're just doing from x values of 0 to 8. and that area is 12, then what should the area have been from the 8 to the 10?
Oh, she needs
5. Yeah. 17 minus 12 is 5.
So which one of these is that? Is that?
And that's using 6. That's using number 6. And so it's saying if they started here, this is the one where they said from 0 to 10, and this is the one they're saying from 8 to 10. And so that means that this one must have been 0 to 8. 0 to 8, 8 to 10 is 0 to 10.
Is it tracking just one's on the other side?
Yeah, let's write it out. We'll write it out like number 6. So if I think of it this way, I'm going to say the integral from 0 to 8 f of x dx plus the integral from 8 to 10 f of x dx, right? 0 to 8 and 8 to 10. That should equal from 0 to 10. So don't break it up in two pieces, just call it one big thing.
Should it be the other way around?
We're setting it up to look like number 6 instead of doing a subtraction problem. So I'm making it look like the property from number 6. And then if you plug the numbers in, 0 to 8 is 12. So I'm saying 12 plus what equals 17? And it's definitely 5.
It might be 6.
I keep writing a fraction, but then you write
Okay. How are your brains?
Dead.
They hurt?
Like, I don't, this doesn't
My brain didn't look too big.
Yeah.
My brain's not that bad.
All right, here is the last one. Are you ready?
You crazy.
All right, this one is going to be a little picture of a graph. You don't need graph paper, but just be careful when you draw it. Okay, there's the graph that you're drawing. Isn't it a cute little graph? This is at 1 right there. That's a height of 1. And the instructions, so this is the graph f of x, you can label it. The instructions are to evaluate the integral from -1 to 3 of this. So what they're asking us to do when they say integrate this from -1 to 3 is they're saying what's the area under the curve? From an x value of -1 to an x value of 3, find the area underneath that curve. So we want to break it up into different shapes. So do you guys see any shapes in this picture? I see half a circle, yep. So here's my,
circle, triangle, square.
there's my half a circle. So how am I going to find the area of this half a circle? So it's pi r squared, right?
Pi r squared divided by
And what is the radius of this half circle? 1. So I know it's going to be pi times 1 squared. And you're right, we're going to divide that by 2 because it's half a circle, not a full circle. So pi 1 squared divided by 2. Okay, what's another shape you see?
triangle and a square.
Okay, I see a triangle. How do we find the area of that triangle?
1/3.
1/2 base on height.
1/2. What's the base?
1.
What's the height? 1. Okay, there's our triangle. And then what was our last shape? Square.
One by one. It looks like a rectangle.
It looks like a rectangle, but we know the sides are the same length. I'm sorry. Okay, 1 by 1. All right, so evaluating this, our exact answer, right, because we just did this perfectly, is this is pi over 2 plus, what's this? 1/2 plus 1. So what is the area underneath the curve?
What about you?
Pi halves plus 1.5 or 3/2, whichever way you want to say it is fine. So that is our exact answer. That's it.
I don't know. It's not really one high.
That's not too
Why
bad.
can't you say pi plus 3?
Patrick, what are you talking
You could say pi plus 3 all divided by 2 if you wanted.
Yeah, that's
You could say pi halves plus 1.5. You could plug it all in your calculator and then say approximately, whatever the decimal is.
What have you ever wanted to see me?
You have the
Which one
power
of
to
these-
choose.
Which property is different?
This wasn't so much a property as just thinking of this as just thinking of it as different shapes if you can, yeah.
So,
It's the visual stuff.